All right. Hi, everyone. It's 10 past 11, so I'd like to start now. I'll wait for another 10 seconds for everyone to settle down. All right, so this is the logistics for today's lecture. And as you can see that everything is same as before, but we are a few days in. The assignment is due in Friday. There's office hours this Wednesday and also Friday from 10 to 12. There will be TA office hours. So if you have, please utilize the office hours if you have any questions. But I'm hoping that won't be necessary because everyone here is already done. So yeah. The final exam date has been announced, April 22nd, 2 to 5. I think it's at the Medical Sciences building, but it depends. Like there's 2 rooms, depends on your last name, I think. Please check the department website. Yeah, so with that, today's lecture plan is we'll continue with hidden Markov models, and we'll have one more lecture on hidden Markov models. The last one will be this Wednesday. If you recall that we're still in task 1, I think we finished forward procedure and we sort of glossed over backward procedure a little bit. Today we'll finish the task 1 and task 2, which is, if you recall, is the task of inference. So just as a recap, there are 3 fundamental tasks that we want to look at. The first one was just calculating the overall observation likelihood. And the second one was the task of inference, where you're trying to figure out the best possible states or Q star that gave rise to the observations. And the third one is the task of training, where you have observations and you're trying to update your theta values using the observations. Okay. And yeah, so let's recall that in task 1, our point was to calculate this guy, observation likelihood. And here, this is a mathematical formalization of that. And this is broken down using the HMM definition, okay? So the joint probability of observation and state sequences Q can be broken down using pi, which is the initial state probability, the emission probabilities, and the transition probabilities. So in the forward algorithm, you saw this, we did this from left to right. And we can chunk this as follows, that basically, after the initial state, time t equals to 0, we are using this same sort of sub-problem over and over again. Like here, you have the transition probability and you have the emission probability. And omicron, or O, represents whatever the observation is. The little subscript here shows the time step, okay? So we know how to do this forward way. And we also said that we can repeat the same thing, but in a backward manner. And we talked about a little bit that why do we need to, in order to calculate the observation likelihood, we don't need both of them, but we'll be using this backward procedure later in task 3 to when we're doing expectation maximization. So essentially, we just pause that question if you have it, that why do we need the backward procedure for a second, and then we'll get back to it when we actually use it, okay? So this picture over here shows that basically we're doing the exact same thing. We're trying to find the observation likelihood, but now we're going from left to right, or from the final time step, which is t minus 1, because our timeline is 0 index. We're going from 0 to t minus 1. T minus 1 is our last time step, okay? And so we see over here, if we start with the last time step, then we have some emission probability. So we know what the observation is. So let's say we observe something which is omicron, and B, this gives us the emission probability of that word, okay? And then, as usual, we have a transition probability. So you're coming from t minus 2 to t minus 1. So that is the transition probability denoted by A. And then we multiply by that the emission probability of whatever I'm observing at t minus 1. And we can repeat this the same way as forward procedure. Now notice that we have introduced another Greek letter. It's beta this time. So beta is exactly similar to alpha, but from the backward direction, okay? So we're calling this as our beta t minus 2. So think of beta as you're standing at a time step t, and then beta captures all the probabilities of your future observations. So if you're a node, it just captures all the probabilities of the outgoing arcs. And alpha was more like from left or from the past to the future. So beta gives you everything that's in the future, okay? So yeah, so this is the formalization of beta. Beta is the probability of starting in state I at a time t, then observing everything that comes thereafter, okay? So you can also visualize this as computing or summing the probabilities of all outgoing arcs from that node. And here we have the mathematical formalization. So yeah, so the probability you're standing at time step t, and let's say you are in a certain state Si, and then it gives the probabilities of all future observation that comes thereafter. Okay, so from t plus 1 to our final step, which is t minus 1. All right, so just like forward procedure, we have 3 steps for backward procedure. We have the initialization, induction, and conclusion. Okay, so in backward initialization, we use the last time step, so this column over here, and we initialize our beta I values for t minus 1 as 1. Okay. Now you may ask the question that where is this 1 coming from? So there isn't a good probabilistic interpretation for 1. It's more for algorithmic convenience, and you'll see that how setting it to 1 in the end everything falls into place. And so this is more of algorithmic convenience. We initialize the last column, the beta values for all the nodes as 1. Okay. Now, then we have the backward induction. In this step, we calculate all. So this is in this example, let's consider this specific node in yellow. Okay, let's say we are in state I and time t. So in this case, our I is S2, and our time is t minus 2. Okay, so the ideation is the same, that we'll try to basically calculate all the probabilities of the outgoing arcs. So all the state values over here, what is the probability in this yellow node, okay? So the way we do this is Aij is the transition probability, and the observation probability, this is the emission probability of observing that whatever the observation was in the future, immediate future time step, okay? So these two guys are familiar, we've already seen that. And then we also take beta j t plus 1. So beta j t plus 1, for example, like this node over here, beta j captures the probability of all future probabilities of that node. So essentially using this mathematical formalization, we're summing all the probabilities of all outgoing arcs from this specific node. Any question? So you can do this for all the nodes over here, but here we're just on this yellow node here. So yeah, so this is very similar to the forward procedure, just the reverse direction. And we have the conclusion step, which is when we're at time equals to 0 or the first time step, we just sum over all possible initial states, which gives us our observation likelihood. Okay? And as you can see that in our first time step, when t equals to 0, we utilize pi, which is the initial state probability. So if we're in a state I, then initial state probability multiplied by the emission probability of observing omicron 0, or our observation at time step 0. And then we multiply by the beta value, which captures all possible future probabilities. So together, if we sum across all the possible states, gives us our observation probability of P0 given theta. To summarize, the backward procedure has 3 steps. First, we have the initialization step, where we set the beta I of the last time step to 1 for all the states. Second is the induction step, where we calculate the probabilities of a node at state I at time equals to t. And lastly, we have the conclusion step, where we essentially sum across all the nodes of the first time step, which gives us the observation likelihood. Yes?
But if, for example, we used some other constant for initialization of t minus 1, wouldn't that basically result in the conclusion probability being multiplied by, say, 3 or 5? We can get any conclusion probability by choosing initialization value, can't we?
That is right. Yeah, so the pi I value will obviously, it matters. The initial state probability will change the overall observation likelihood.
No, I mean, when we set the last one to 1, so you said that it is kind of arbitrary. And
so 1 is basically, think of 1 as not in terms of probability, but as a constant that doesn't modify anything. So it's almost like, because if you set it to any other value, like 0 would cancel everything out. Like 1 is just, we're just the starting point. It just, if you multiply anything by 1 is the same thing. So don't think of 1 as a probabilistic convenience. It's just, probabilistic interpretation is just a convenience.
But if we set it, for example, to 3, won't it affect our conclusion? The probability of the observation, won't it be multiplied by 3?
If you set at the initialized step, if you set beta I as 3,
that will basically propagate.
Of course it will. But why would you pick it as 3?
But is there any particular reason to pick it as 1? Because if we can...
So the reason being that, like, it's a constant, it doesn't affect anything.
I got it. So basically there is the probability of these observations, then there are probabilities of other observations.
Yes.
And then we would normalize them anyway so that they all sum to 1.
Right, like they are the same probability like for each of the states, and yeah.
Yeah, got it. Thank you.
Yeah. Okay, so then we again ask that question that why do we need this backward procedure? Because forward procedure gives us what we want. And as I alluded to earlier, that combining these two procedures will be used for solving some other tasks, as we'll see in task 3, where we try to do parameter re-estimation of our model, or in the training task. So, and also the fact that alpha and beta, when combined, we can get the observation likelihood at any point in time. So if you're just doing forward procedure, you have to go all the way to t-1 in order to get the observation likelihood. If you're using the backward procedure, you have to go all the way to the first time step in order to get your observation likelihood. But as you'll see over here, that if you have alpha I and beta IT, then you can have a trellis, and you can say that, well, what is the probability? Like you can just point to a single node anywhere in the trellis and say that, okay, so give me the probability. So if you look at the first equation over here, that essentially is pointing to this middle node over here. It's saying that given my observation, and I'm in some state I, what is the probability of the observation, of all the observation given I'm in state I at time time t equals to 2. T equals 2, and then you can just call alpha I2 and beta I2, and that gives you the answer, okay? And if we wanted to get the observation probability of all, like the observation likelihood at time step equals to t, we just do sum over this column, and we're done, okay? And we can do it at any time step. We can do that for time t equals to 1, 2, or anywhere like in this trellis. So that is the advantage of having alpha and beta. Okay, so with that, let's move on to the second fundamental task for HMM, which is the main content for today's lecture. So this is the task of inference. So we're given an observation sequence, and we have a model parameterized by theta. Then we're asking that what is the best possible hidden state sequence that will give rise to this observation that we're seeing, or what are the state sequence that best explains our observations. So yeah. And what is the purpose of this is like asking the question, what is the purpose of inference? So we're trying to infer, we know that there are certain hidden states, and we're trying to infer that what is the possible state sequence, because our state sequence are non-stationary. So essentially, we're trying to find Q star using our observation. And in the forward algorithm, we did not care about specific state sequence. We just summed over all possible state sequence. But in this task, we do the state sequence matter. We're after the best state sequence. In mathematical, if we formalize this mathematically, then it becomes Q star argmax Q over the joint probability of observation and state sequences. And the bottom equation basically decomposes the joint probability using parameters of an HMM, like the initial state probability, emission probability, and the transition probability. You have already seen this in our forward and backward procedure. Let's look at some real-world applications that why or when we'd need to choose our Q star. So yeah, so if we consider at the bottom, you'll see some real-world applications of using HMM to infer the hidden states. So if you consider that everything that I'm saying, the words coming out are being generated by an abstract layer of parts of speech, which are giving rise to these words, then we can infer that what are the sequence of parts of speech that gave rise to certain sentence or that I'm speaking, or the certain sentence that's written. The same thing applies that, you know, if I'm saying something, your observation is in English, but it could be, it's being generated by some underlying mother tongue or French or whatever. That's the translation task. And same thing goes for encryption, that you're observing encrypted symbols, but behind that, there's some hidden variables that conveys the actual message. Okay? So as a concrete example, let's continue with the parts of speech state sequence. So here our observations are the word, is the sentence or phrase, will the chair? Okay? And the hidden variables here are the abstract parts of speech that are generating this phrase. Now chair here, as we know that chair could be like a conference chair who's chairing a conference. So in that sense, it's a verb, right? But usually chair is, if we just use it in isolation, chair can be inferred as a noun. So if we scrutinize both this variance A and B over here, then we can conclude that the second chair over here is actually a verb and not a noun. Okay? So this is an example of how, like, you know, you can have, so in this case, you have two possible state sequences, okay? A and B, like, so MD, DT, NN, and VB is one state sequence, and the second one is the second state sequence. But what we're after is the Q star here. So our argument is that this Q, or possible state of sequence, will have a higher probability than this state sequence. And this is what we're trying to get in this task, okay? Okay. Now, recall that the observation likelihood depends on the state, the underlying state, and then this underlying state is non-stationary, meaning that this state changes over time. So if we go a naive way of explaining the state sequence, we can say, let's say we have the observation stops, and we can say that, okay, so let's look at the emission probabilities, and it looks like tops has the highest probability when we're happy, so the underlying state sequence is happy, okay? But this naive approach doesn't work. The reason being that the underlying hidden states is non-stationary. You could be switching states, and there's no guarantee that you will be in happy state and just grab that emission probability, okay? So the naive approach doesn't work. We need something more sophisticated. And this is where Viterbi algorithm comes in. This is a very famous dynamic programming algorithm, and there are many variants or in different subdomains. But essentially, we'll work through this algorithm through an illustrative example that I'm hoping that you can help me with along the way. And we'll be introducing another two Greek variables. So you'll have a few Greek variables to remember from the HMM lectures. So then we're introducing delta IT as the maximum state sequence probability at time t, okay? So this will be like, this is defining the subproblem. So it's a dynamic programming algorithm, so you will be structuring it as a subproblem that we like solve by caching like the results of previous subproblems. And psi t is basically a backtrace label. So psi t is not a probability. Psi t is just saying that it's a label that what was the best previous state that we came from, okay? So delta IT is a probability, and psi t is just a backtrace label that has a pointer to the previous best state. And you get the idea that when we finish it, we'll just read off this backtrace, recursively read off backtrace, and then we have our best state sequence, okay? Okay, so let's look at an example to illustrate this. And will we use this as our running example? Yeah, so these are the emission probabilities per state. For this running example, just notice or maybe remember that you don't have any arrow. So the three states are D represents disgusted, S is sad, and H is happy. There are no arcs from sad and happy states back to disgusted. So like remember this. So the transition probability of say SD or HD is 0. All right, so with this, let's see how we can do this. So the first step of Viterbi is the initialization step. And the initialization step, we simply calculate our delta I values using our initial state probabilities and our emission probability of observing O0, whatever our observation is. And yeah, so it's just the initial state probabilities multiplied by the emission probability of the initial first time step observation. And we set size 0 as 0. So 0 is basically a non-label. 0 does not signify anything. It just means that you are in the first step. There's no previous steps to point to. It's just null. Okay? And our goal is to basically reach, in this case, we just have 3 time steps, meaning that we have 3, our observation consists of just 3 words. And our goal is to basically reach here and select the delta with the maximum probability and use psi to just read off the state sequences that gives rise to that max probability. Okay? All right, so let's make this concrete. So we're given our initial state probabilities. Pi d is 0.8, pi h is 0.2, and sorry. Okay. All right. So and pi s has to be 0, I guess. Is there a typo here? No, there isn't. Yeah. So then how do we initialize? We're just multiplying pi d with, what's this? So if our initial probability for happy state is 0.2 and our initial state probability of disgusted is 0.8, and then to initialize, we multiply initial state probability with the emission probability of the first observation. So our first observation is ship. And we're basically multiplying this pi with the emission probability of ship across each of the states. So if you're in a disgusted state, sad state, then our emission probability of ship should be 25. Let's just check if that's right. So happy state, ship, 0.5. Okay, makes sense? All right, we're on the same page. And our observation sequences ship, frock, and tops. Okay, so next step is the induction step for Viterbi. And this is basically, we'll be focusing, so it's the best path to state Sj at time t, which is delta jt. And that depends on best path to each possible previous state, delta it minus 1, and their transition from I to j, okay? So if we consider this over here, let's say we're in happy state, or no, this is just a generic, this is a mathematical formalization. So if you're in state j, then you take the max of delta I of the previous state, all possible previous state, in the previous time step t minus 1, multiply that with the transition probability between state I to j. And then notice that the emission probability is outside the max operator because it doesn't matter, it's constant, right? So our observation at t is fixed and the emission probability in state j is fixed, so it's outside the max operator. So the only thing we're concerned about this previous steps delta value, and the transition value of delta between state delta I and j. And in the bottom we have the backtrace operator, which is basically just it's going to cache whatever this delta, like whichever state is our max state. Okay, so we can use it as a max as a backtrace label in the end. Okay, so this is just storing the information. Okay. So as an example, if we're in time step 1, and it happens to be that we are coming from state disgusted in the previous time step, then the label, the backtrace label, would just store D here, okay? All right. So let's make this more concrete. So this is for all the 3 possible states in this running example. So in the first, when we're in a SAD state, our delta SAD at time step 1 will be the maximum of the previous time steps deltas multiplied by the transition, the state transition probability, and the emission probability of observing froc when we're in SAD state, okay? So basically delta I0, so basically we'll pick this delta values, which is the top row, multiply that by the transition probability. So we'll have 3 transition probabilities here, SAD to SAD, happy to SAD, and disgusted to SAD. And then we'll take the max of whichever path and then multiply that with this constant. And then we'll basically store the state that gives us the best possible previous state in our backtrace label, and is the same for the next 2 states, okay? Does this make sense? Any questions? Maybe, yeah, so then quickly let's take a specific example. So now we're dealing with this particular, so we're disgusted state and time equals to 1. Our observation is froc, okay? So what we do, we take the delta i's, I represents all the previous states, and the transition probability. So if we are in disgusted state, we're interested in SAD to disgusted, happy to disgusted, and disgusted to disgusted. Remember at the start of the example, I said that the transition between from SAD to happy to disgusted is 0, so we can't go there. So this actually basically cancels out the first 2 possible states right away. But essentially, AID is like this 3 transition probabilities. We multiply that by the delta of the previous time step, which is at time step t equals to 0, like t minus 1 is 0 here. So delta SAD 0, delta H 0, and delta D 0. And these are the corresponding values. Multiply them. The first 2 become 0. So obviously we have a winner here, which is delta D0 multiplied by the transition probability of disgusted state to disgusted state, which is 0.032. So if we take a max on this 3, our max is the bottom guy over here, and we have a winner. So we'll just multiply 0.032 with the emission probability of froc at state disgusted. And in our backtrace label, we'll store what? Disgusted. Yes, that's right. We'll store disgusted or D over here, okay? And we see that that is the case. This 1.92 comes from the multiplication of 0.032 with the emission probability of froc, and we stored that as our delta D1. And this is our backtrace label. So this should be like crystal clear. And we continue. So now we're dealing with a state happy at time equals to 1, our observation being froc. We do the same thing. And we get the values. So in this case, if we look at the yellow box over here, so we'll look at the transition value. So we're in happy state. So we'll look at the transition value from SAD to happy, happy to happy, and disgusted to happy, okay? And then we'll multiply by the previous time steps delta values. So delta SAD 0 is given by this guy over here, which is 0. Delta H0 is given by this guy over here, which is 0.06. Delta D0 is given by this guy, which is 0.08. You multiply that, and you perform a max operation on these 3 values, and you see there's a winner, which is delta happy 0 and transition from happy to happy. And in this case, what do we store in the backtrace label? Do you have an, like, what do we store in the backtrace label here?
H.
H, yeah. Yeah, okay. All right, so then we keep going, and this is for the sad state, and we do exactly the same thing. We have a winner, and in this case, we can see that I think happy to sad is the winner. So we want to store happy here as the backtrace label. Okay, very straightforward, and we can keep doing this, and then we calculate here we're in state disgusted time step equals to 2. Okay, so in this slide, there is a typo here. Sorry, in this slide there's a typo. Can someone tell me what the typo is? Yeah.
A of I to disgusted instead of sad.
Yeah. Yes, and is that it?
Emission probability of
Yes. Yeah. Yeah, that is correct. So if you see that here the transition probability and basically the subscript S should be D, I believe, in here. Right? Because you're in state disgusted, and the transition is like it should be D over here. That is a typo, and you know, instead of like I'll revert this situation into my credit by saying that this typo was introduced intentionally to change your listening from passive to active. So it's not a bug, it's a feature. But I'll correct this slide, and post it, or yeah, okay. All right, so here, so this is exactly the continuation of the same thing, and then we basically, once we finish the induction, this is what we have. We can see that like you have the backtrace label here, and whatever was the maximum probability, like the delta values that we saw earlier, and we're ready to go to step 3, which is the conclusion of Viterbi. And this step is easy. You simply pick the best value, the best final state. In this case, this is the highest probability or the highest delta I value. And then you recursively can do a backtrace on the psi operator. And that will give you DD0, or the best possible state sequence, okay? So yeah, you just call psi recursively. And yeah, so and your sequence probability becomes your observation and Q star and you know the max size, so whatever the probability of this sequence is. Just like any this kind of problem can give rise to a situation where you have equal probability between two final probability states, and you can apply any heuristic algorithm to break the tie, like simply randomly picking one of the two best possible option. Okay, so any questions about this? Okay, so if there are no questions, why don't we maybe break the monotony with a quick brain teaser? Now, before this, how many of you have seen this puzzle before? Okay, so then you don't get to answer. All right, just one. Okay, all right. So let's spend a minute on this simple puzzle. Of course, your final exam questions will be not as easy as this. Okay, 10 more seconds. Then we'll do a poll. All right, let's do a poll. Or any answers? Any guesses?
Not enough information.
Okay, what's the answer?
I thought say yes.
Okay, any other answers?
Not enough information.
Sorry?
Not enough information.
Not enough information, okay. Who thinks it's a no?
I know that.
Is it a no? Okay, so you don't get to answer. Okay, all right, so accepting him. All right, so we got one yes, we got one not enough information. And if we were to do a tie breaking, how many of you would randomly pick no as an answer? Okay, or maybe not interested in this question at all. Okay, so yeah, so the right answer is, so basically Anne is the central figure here, and Jack is looking at Anne. So the only information we know is that Jack is married, but George is unmarried. Okay, so if we hold those two variables, and then Jack is looking at Anne, and Anne is looking at George. So Anne can be either of married or unmarried. So if Anne is married, Anne is looking at George, a married person is looking at an unmarried person, so the answer becomes yes. If Anne is unmarried, then Jack is married. A married person is looking at an unmarried person. So the right answer is yes. All right, good job. Okay. All right, so let's continue with the actual slides. And yeah, so essentially that was the conclusion of Viterbi. So just to recap, Viterbi has 3 steps: the initialization, induction, and conclusion. And you're trying to maintain like 2 Greek variables. Yes?
So in conclusion, like Viterbi is telling us what is the most likely hidden state configuration.
Yes.
So we would say it's DDH in this case.
Yes. D.
H, right?
So no, because in this case, I guess, no, we're going D, right?
But that's the previous, like we end up in.
So you'd start with the disgusted state, and then you're in disgust. DDH, sorry. Yes, you're right. Yeah.
So what's the answer?
Sorry?
So what's the answer in the sequence?
So in this case, the sequence would be DDH. Yeah, because the backtrace operator gives you the previous state, right? So D here points to the previous step, which is D, and this points to the previous step, which is D. So, but you can know that like the max from your conclusion, because delta I maximum, right? You know that what is the max operator gives you. So it's, yeah, it's going to be DDH, right?
So it's like from the
Last.
end, and when we see 0, we check out the row.
Yeah, so basically if you're in the last conclusion, you already know what is the max, which state is the max, and then you call them max, so backtrace to give you all the previous one, starting with, T minus 2 and whatnot. Right, so yeah, so that was a good recap. You have 3 steps. You have a delta variable and a psi variable. Delta variable captures the probabilities, and the psi basically is a backtrace operator that allows you to like call it at the end in order to get the best possible configuration. All right, and this is a side slide. It just explains why you see a lot of like, we use the log domain in actual solving problems or coding and whatnot. And the reason we formulate this probability calculations into log is because firstly, it's just an equivalence surrogate objective function. So if I say that if our objective is to maximize observation likelihood or maximizing Q star is the same as minimizing the negative of that probability. And by converting into log, we give it more numeric stability, plus also computational efficiency, because if you remember, then in the log domain, we're converting the multiplications into summations. So it's a cheaper computationally. Okay, so the third task for HMM is the task of training, and we'll be using expectation maximization, specific expectation maximization algorithm to do it. We'll probably just do the first we won't be able to finish it today, but we'll take a look at how it looks like, and we'll finish it off on Wednesday. Before we proceed, how many of you have seen some kind of, or implemented some kind of expectation maximization algorithm by now? Yeah, that's about, like, it should be like, by at this time, I guess 4th year, you should have been exposed to EM algorithm. This shouldn't be completely new to you. But yeah, so essentially in this problem, what we're trying to see is that we have our training data or observation sequence Omicron or O, and we're trying to basically reparameterize, like we're trying to get the theta star, which consists of the initial state probabilities, the transition probabilities, and the emission probabilities. Okay, so we want to modify the parameters of our model theta so that our observation likelihood is maximized for some training data. So argmax, this is the mathematical formalization, argmax theta of our observation likelihood. Yeah, so why is, the answer is that why do we train a model? Like, we're trying to get the a trained model that best fits to our observation data, so that with the hope that it works best, that would be the parameter values that works best on some unseen test data. The basic question of like training any model. So this just shows that the decomposition of the joint probability of observation and state sequence that we have already seen before. And this breakdown should remind you of like the bigram probability when we did language modeling. If we knew, like if Q was known, then we could have just done like a maximum likelihood estimation using this decomposition. The training data, if the training data had like, you know, the state sequence, like if we had all the information, the point of this slide is that if we had all the information, we can just do a MLE objective in order to get whatever we want. We can calculate our theta values from there. But we don't know the states, and we can't count them, and we have to do something more sophisticated. Okay, so and that's where iterative hill climbing or expectation maximization approach comes, where we can guess what counts as a good theta value, and from there we can iteratively, like, you know, using our data, we can make that theta better. So for example, you can already see where we're going with using a good pre-existing model. So it could be some initialized values of theta, and then that could be our good pre-existing model, and we sort of use EM to iteratively make it better. So if we knew theta, then we could make expectations. So here theta is the HMM parameters like initial state probability, emission probability, and observation likelihood, etc. Observation probability. And if we knew theta, then we can expect the number of times we're in certain state, and we can also make expectations of the number of transitions between states. And if we know those two, then we could compute another maximum likelihood estimate of our theta. So, and if we calculate theta, we can use that theta to again make a new expectation, and then basically repeat the process. And in an expectation maximization algorithm, we usually do we continue the iterative training process until some convergence or stopping criteria is met. Usually, the convergence is some kind of difference value threshold. So if we observe that between our iterations, the values of theta or our parameters are not changing much, it's almost remaining the same, then we say that, okay, so I think we have reached an end, and we call it a stop. But there could be other convergence or stopping criteria where you can basically set the number of iterations beforehand. Okay, so in this case for HMM, the algorithm we'll look at is called Baum-Welch. And Baum-Welch is a specific version of expectation maximization algorithm for HMM. It's also known as the forward-backward algorithm. And it has 4 steps, but the 3 main steps we've seen sort of we see in all EM algorithms. So first you initialize the model, and then you have expectation step where you compute the expectations for state transition and compute the expectation for emission based on some given model, which is parameterized by, let's say, theta k, if we're in the kth iteration. And then in the maximization step, you update those theta parameters, like our start, transition, and observation probabilities, to maximize the likelihood of our observation. And then you keep repeating this. Now, one possible con or disadvantage of using iterative hill climbing, or specifically in Baum-Welch, the initialization really matters. So as you can see in this figure over here, that you could, depending on your initialization or start point, you could end up in a suboptimal maximum point or a local maxima. So the first step is Baum-Welch initialization. So the initialization, there are many different ways, like few possible ways you can initialize the initial theta 0 parameter. It could be just a uniform probability distribution where as you can see, that all of them have the same probability. Yeah, so that's one way to do it. The other way to do it would be to just randomly pick probabilities for the emission probabilities in each state, as long as it satisfies the condition of being a proper probability distribution, which means that all of these probabilities should sum to 1. And another thing you notice is that all the outgoing arcs in the state transition probabilities, they sum to 1. Or you could also use some kind of prior distribution for setting your emission probabilities for the states. And in this kind of like prior distribution, that would require some kind of pre-clustering, like k-means clustering. So if you have 3 states, you do like k equals to 3 clustering, as shown by this figure over here. And then basically you can pick the probability of the words in each of these clusters. Okay. And so then we move on to the expectation step. But maybe I think this is a good place to stop for today, and we'll take it on from here on Wednesday. All right. Thank you.